the Internet of Things and industrial Internet of Things now comprise many billions of connected devices, and we're talking sensors of all kinds that send data that they collect back to CPUs for processing. But unfortunately, networks of every description really tend to draw bad actors who are looking to infiltrate them, whether it's for a malevolent purpose or just for hacker cred. So that means there's plenty of cybersecurity challenges for developers and system integrators to stay ahead of. But how do we ensure that industrial IoT networks are sufficiently encrypted so as to preserve the integrity and confidentiality of the data flow?
Right. So my expertise is in the industrial side. So most of my time is spent on the shop floor, actually dealing with PLCs, controllers of machines, legacy systems. We still see Windows XP, Windows 95, because those assets last a long time. So you don't really have a choice. And if we talk about encryption, then we have to talk about the protocols that are being used on the shop floor. And it ranges from Modbus to Ethernet IP to backoff to whatever. And from our experience, those were never designed to be secure, both from like a tunneling perspective and even in the payloads themselves. Being deep on the south side where we're actually doing connectivity, you don't have a lot of choices, I don't think. But then as the data starts to move through the pipeline, through the enterprise, then you have an option, because now we're dealing with more modern IT networks. So that's kind of my take on that.
Okay. And Steve, you had a thought on that?
I do. I think we always have to come back to risk. What level of risk are we dealing with, and how can we manage that risk? And so when we're dealing with IIoT and industrial equipment in general, there are lots of different ways that we can manage the risk. A particular network, and we have to keep this in mind, that in industrial environments, there's a reason why protocols like Modbus were not originally designed with security, because the assumption was they're within a secured, physically secured environment.
Mm-hmm.
And if that's true, if they're used within a physically secured environment, then we don't need to encrypt that network, because the bad guys aren't going to get into your plant and tap that network and decrypt or inject data into that network. Now, when we change that assumption, when we start moving data outside of the plant, and with industrial IoT, we're moving data outside of the plant in many cases, it's often going back to the cloud. Then it's that network, that connectivity back to the cloud, which is going across a no longer trusted network. So it's not wires within the plant, it's up to the cloud. And that connection definitely needs to be secured. If you're going to use wireless networking within the plant or within your industrial setting, then you also have to worry about the possibility that somebody using a radio antenna, maybe a high gain antenna, might be able to capture your wireless network traffic and decrypt that and use that to their advantage, and then maybe even inject some messages back in, stop, 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 and they're shutting down the plant, which you didn't really want. Or they could even do something more malicious and jam messages that are critical to maintaining the safety of the plant. So when we change the assumptions, then we have to make sure the security is adequate to manage the risks that we need to manage.
We'll move on to a mitigation of hardware risks. How do we do that in IoT and IoT networks that can introduce the vulnerabilities to threats?
So we do a lot of thinking at Infineon about hardware risks. We have 30 plus years of experience building secure hardware. So that includes the chips that go into credit cards and passports and industrial systems and networks and routers and all sorts of things. These are specialized security chips, and they're designed to resist what are called physical attacks, where somebody is actually getting their hands on the device and they're tampering with it. Now, in some industrial settings, that's not something that you need to worry about. The likelihood that anybody's going to get into that physical space and tamper with the device is pretty minimal. But in other cases, that is a concern. So for example, consider the electric grid, or anything where it's a utility and there's lots of distributed infrastructure out there in the field. People can actually break in and tamper with one individual device. And so then you do have to worry about physical attacks on something that's at the top of a pole, or something that's in a cabinet out in the field. So when we think about those, what vulnerabilities we're trying to protect against and what sort of physical attacks can take place, it really depends, again, on the context and what additional security measures you have. And then we come back to risk management again. If the bad guys are able to get in there and tamper with something, how much damage could they cause? Is it going to be a real disaster? Or is there some way we can manage it and say, okay, we know that just like some transformers are going to blow out in the field, that there's going to be some cybersecurity compromises which will take place out in the field as well. And we just manage our system with that in mind, so that we have the circuit breakers, so to speak, literal or figurative circuit breakers, so that if there is an attack out in the field, we manage the risk, we detect it, shut that off, send somebody out, roll the truck to fix that problem and prevent it from spreading.
Yeah, I would agree that once you have physical access to the hardware, then game's over. It's whether it's an old piece of hardware or a new piece of hardware, I mean, you could do all kinds of damage. Even with our Shark device that connects sensors to the network, it's secure over the network, but once you have physical access, there's nothing stopping you from rewriting the firmware, introducing malicious code, messing with the data.
Chris, if you don't mind, I'd like to jump in just to say that one of the things that we do with our security chips is to actually make them tamper resistant, and not specific to our product alone, but there are tamper resistant features included in these credit card chips, the same chips that we provide to our customers who make routers and switches, which mean that you can't actually go in there and rewrite the firmware on that device. Now, I'm not saying that's suitable for every application, but just there are some things that you can do to make those devices out in the field more resistant. Not that you always have to do it. And sometimes it makes more sense to say, we're going to take that as a given that sometimes they will be hacked. But there are some options there, at least to know and perhaps to protect your most valuable secrets. If there's some cryptographic key, some secrets on something that you just can't have falling into the wrong hands, you can put that in a security chip, for example.
Right. And I guess I was thinking of like the infamous case of the Nintendo Switch, where they got it was supposed to be secure, but somehow, some way, somebody found a way in through, I don't know, was it the video card or something like that. And to me, that's just insane how you have to think of all this risk and you still miss it, right? It's kind of crazy.
We never can make something perfectly secure. You're absolutely right about that. And that's why it's a both and kind of thing. We secure it as much as we can, and then we plan for what if the worst happens and somebody breaks in. How do we reduce the impact of a hack?
Yep.
There's a lot, people are very creative, right? There's lots and lots of ways to break something. There's usually only one way to design it right, but they can break it in a myriad of ways.